In this video, we build upon our previous concepts of probability, talking about what it means to have one event that depends on another. In other words, what's the probability of getting a red king given we know that it's one of the clubs, right? That would not be very high probability. It'd be zero, in fact. So today we're going to talk about conditional probability. Let's start off with a formal definition. In order to get our definition here, I want to remind you of our previous video when we talked about the probability of and. We said the probability of A and B was the probability of A times, remember and meant multiply, the probability of B, and then we had this line here that meant given. Do you remember that? You can go back to your notes or watch that video again. Given that what happens next has already occurred. So given that A has already occurred. In other words, if you're drawing two cards consecutively from the same deck without replacing the first, we're saying that the first draw impacts the second, right? So that was how we found our probabilities last time. Now, when we talk about the conditional probability formula, what we're actually doing is nothing new here. If you look at that old equation for probability of A and B, and if you were to solve for the probability of B given A, so this part of the equation here. Now, if you remember a little bit from your algebra days, I'm not trying to trigger anyone who's a little bit scared of algebra, but you can undo multiplication in an equation with division. So I could get this part by itself, the probability of B given A, by dividing both sides of this equation by what is next to it, in this case, the probability of A. So if I want to get the probability of B given A by itself on one side of the equation, I would have the probability of A and B together divided by the probability of just A. In other words, the letters are not very important. What's very important is the position. Whatever comes after the given, that's the probability that you are dividing by. So if your textbook says something a little different, has different letters, things are in a different place in the formula, just keep in mind what matters is the position after the given sign, right? After the given, that's what the probability that we're dividing by, the probability of that letter. So what that would be saying is, in order to find the probability of an event B, given that event A has already occurred, we would need the probability of both A and B occurring at the same time divided by just the probability of A, okay? Now let's go ahead and see that in real life, okay? So consider your six-sided die, right? It has the sides 1 through 6 on it. And we're saying here the probability of rolling a 2 on a six-sided die. Well, we know how to find the probability of rolling a 2, right? There's 1, 2 out of 6, so the answer would be 1, 6. But notice there's a word here after that comma, and it's given. Given that you know that we've rolled an even number. So someone is telling you, we know it's even, what's the likelihood that it's also a 2, okay? So the way we would write this would be the probability of rolling a 2 given the fact we know it is even. According to our formula above, we'll do things the formula way at first, and then I'll show you a little shortcut. You would need to first find the probability of both A and B. So in this case, you would need to find the probability of rolling an even 2. So even and 2. So an even 2. Okay, you could write even and 2, 2 and even, however you like to say this, but usually in English we would just say an even 2. That takes care of this part here, right? The numerator. And then next we would be dividing by the probability of A in the formula, which in this case, what comes after the given sign. So I'm dividing by the probability of getting an even number when I roll a die, okay? So what would this look like? Let's take a look together, shall we? The probability of rolling an even 2, well, let's think. How many even 2s are there on a six-sided die? Well, there's only 1, 2, and it happens to be even, right? So those events are actually happening at the same time. So if you said 1 out of 6, you would be correct. But I'm not done yet. I need to divide, according to my formula here, divide by, let me grab the right color so you can see it with me. I need to divide by the probability of choosing an even number, rolling an even number on my six-sided die. Well, how many even numbers are there? Remember, the even numbers are 2, 4, and 6. Those are my even numbers on a fair six-sided die. So there are 3 of them out of the possible 6, right? So 3 out of 6. And if you remember from our previous video or from your algebra experiences in the past, when you have one fraction divided by another, this is called a complex fraction. And if those denominators are the same, when you end up multiplying by the reciprocal or keep, change, flip, they teach you sometimes, because the denominators are the same, they wipe out each other. Okay, you would really have 1 over 6 times 6 over 3, and the 6's would cancel. So you're just left with 1 over 3 as your answer. So the probability of rolling a 2, given the fact that you know you've rolled an even number, is just 1/3. Well, does that make sense based on what we know about the even numbers? Well, yeah, there were only 3 even numbers to begin with, right? So if I had just started, here's my little shortcut you might want to make note of. If I had simply started with my given, so that's what we're saying here, start with the condition. If you had started with that, you would know there's only 3 possible even numbers, right? 2, 4, or 6. So instead of starting with the 6 possibilities for the die, I would start with the 3 even numbers. Out of those 3, how many of them are favorable to what I would like to happen? How many of them are 2? Well, just the 1, right? So 1 out of 3 would be my answer for this conditional probability problem without having to use the fancy formula. And that can save you a lot of time. So once again, the fancy formula for the conditional probability is nothing new to memorize. It simply comes from the AND formula, but then isolating the probability of B given A, okay? Then if you want to, instead of using the formula necessarily every single time, you could simply start with the given condition, what happens after that line. Start with that to build your denominator, the total number of possibilities in this situation that you're given. And then on top, figure out the number of favorable ways that can happen from that smaller pool. If that makes sense, let's join me on my next slide. Here is one where we're talking again about our deck of cards. So you have your standard deck of 52 cards, and here I've reminded you on the screen in your slides as well what is in your 52 card deck. You will want to have that memorized after you do a lot of homework. I don't think that'll be difficult for you. So keep in mind that in a standard deck of 52 cards, we have the 4 suits. We have ace through 10, and then jack, queen, king. And then, of course, the face cards are sometimes called picture cards, are your jacks, your queens, and your kings, and that the aces are typically low, referring to 1 when we're talking about probability in our course. So here we noticed we're talking about 1 card being drawn. So 1 card is drawn at random, and we are asked what is the probability that it is a king, given, so then we have this new piece of information here, that it is a red card. So what is the likelihood that when I take my deck of cards and I pick one of them out, that this card will be a king, given the fact I know it's a red card? Okay, so let's first start with the formula, and then I'll show you the shortcut, and you can kind of pick what you prefer. Because if you're doing your homework using the textbook or the online homework system, they're going to show you it this way. So I want to make sure you are comfortable with the formula before we do it with the shortcut in the future. So the first thing we would note that for the probability formula for conditional probability, the probability of B given A, and again, it doesn't really matter which letters you use here, what matters is the placement after the given sign, is the probability of both happening, so A and B, divided by the probability of whatever the condition was. In this case, that would be A. Okay? So this is the formula if you are doing it according to the textbook or your homework website. That's how they're going to show you. So we would begin by saying, what is the probability of getting a red card and a king? In other words, what is the probability of getting a red king? Wouldn't that be a short way of saying a red card that is a king or a king that is a red card? Yeah, a red king would kind of make sense, wouldn't it? Divided by the probability of the conditional part, right? Probability of getting a red card. So to do this, I would first have to say, okay, how many red kings are in the deck? You can look at the picture here if you need help, but remember there are 4 kings in the deck. Half of them are black and half of them are red, 2 and 2. So there are 2 red kings out of the deck of 52. For the denominator, it's just how many red cards are in the deck and what's the probability of that happening, right? Well, half of the deck is red. Now you could just say the probability then is 1/2, or you could do it 26 out of 52 before we reduce. The reason this is beneficial to not reduce is because you can see what happens clearly here with the complex fraction. Since 52 is the denominator of each fraction, they will cancel each other out, leaving us just with 2 over 26, which reduces to 1 over 13. Remember, when dealing with probability, you can give your answer as a fraction, a decimal, or a percent. But if you're doing a fraction, what do you always have to do to get your answer right? You must reduce correctly. So 1 out of 13 is the correct answer here as a fraction. Okay, now, is there a shortcut? You know there is. What would it have been? What would I have done differently? Well, I would have first started with the condition. So if I'm using the shortcut, I start right here. How many red cards are there? So I would begin with, well, there are only 26 red cards, half the deck, right? Okay, so I would start with the number of red cards in my denominator, and then I would say, of those red cards, so only looking at the red cards, right, not the entire deck, how many of the red cards are kings? So of the red cards, how many of them are kings? Well, there are 2, aren't there? And then I get the same answer. Eventually, I get 1 out of 13. A lot faster. Let me say that again. I said, where do I start? Start with a given. The given is that I know this is a red card that I've picked. Well, how many of them are there? 26 will be my denominator. Notice I didn't need a whole fraction there. I just needed the total number of the given. Total number of the given, 26. Now, of those 26, how many are kings? Notice I didn't say there are 4 kings because I wasn't looking at the whole deck. I was zooming into my condition, which was that I know I have a red card. That means there's 26 options. Of those 26 red cards, how many of them are favorable to me? In other words, how many kings are there? Just 2. And that's how you can get your answer using the shortcut. I'm going to erase that for now and give us some space for you to try B on your own. Go ahead and pause the video and try it on your own. Okay, you might be thinking, Professor, I think it's the same answer, isn't it? I mean, they look pretty similar. The last answer was 1 out of 13. Let's see if that's what the answer is here. Well, to begin, once again, you need to ask yourself where to start, right? If you were using the shortcut method, you would start with the condition, right? What happens after the given line? So that goes in your denominator. How many kings are there? So they're asking, what's the likelihood that you choose a red card given the fact you know it's a king? Well, there are only 4 kings in the deck, aren't there? So that would be where I would start, and then I would continue by looking in my numerator with the red card. How many red cards are there? Now remember, not in the whole deck, based on my condition. The condition was, I know I have a king, so I'm only looking at those 4 cards. Of those 4 cards, how many of them are red? So if you said 26 here, that wouldn't make any sense. You'd have an improper fraction, which would not make sense because your probability would be bigger than 1, which cannot happen. So that's another clue that something's wrong. So we're only looking at the red cards which meet our condition. The red cards which happen to be king. Okay, well there's 2 of them. So if you said 2 out of 4 or 1/2 would be your actual reduced answer, then you would be correct. Nice job. Again, pause the video and try the next one on your own. It says, find the probability of selecting a face card given the fact that you know you have a heart. Okay, so again, where would I begin here if I'm using my shortcut? I begin with the hearts, right? How many hearts are there? That's one of the 4 suits, right? So did you say 13 for your denominator? I hope so. Now, of those 13 hearts, how many of them are face cards? Jack, Queen, King. Well, there are 3 of those face cards in every suit, so there are 3 hearts which happen to be face cards. So if you said the answer was 3 out of 13, you are correct. Notice had it been 3 out of 12 or 3 out of 14, well, 3 out of 12 in that case, not 3 out of 14. 3 out of 12 or 3 out of 15, something like that, you could have reduced further. But in this case, 3 out of 13 does not reduce. That would be your final fraction as your answer here. Finally, try the last one on your own if you haven't already done so. Okay, it said find the probability that you choose a club given the fact that you know the card is a queen. So again, where did you begin? How many queens were there, right? Good job. So let me come up here. There were how many queens altogether? There are 4 queens, right? So that's one of our nice face cards. So there are 4 queens, 1 in each of these suits. So 4 queens. Of those 4 queens, how many of them happen to be a club? If you say 1, that is correct. So 1/4 or 25% would be your answer there. Well done. Okay, so deck of card questions are very popular. You'll want to get comfortable remembering what kind of cards are in the deck, what is the difference between the suits, those types of things, so that you can be a little bit faster when you're dealing with those questions. But sometimes they're actually going to give you problems based on a table of data. So let's take a look at that in our next example. So this comes from a sample. It might be a little hard to see on your screen here, but in your notes you can see it a little clearer. Basically in this sample here, we have surveyed some women who took a pregnancy test. And I'm going to go ahead and write these down in a little different shade so you can see it better. Here in the first part, we have people who are pregnant, and then we have people who are not pregnant. Here we have people who tested positive, people who tested negative, and then we have our totals. Okay? So let's see what we have here in this chart. For pregnant women who tested positive, there are 100 of them. For pregnant women who tested negative, there are 30 of them. For people who were not pregnant physically, but they happened to get a test that was positive, there are 50 of those. And for people who were not physically pregnant and also got a negative pregnancy test, there were 70 of those. So we have terms when we're talking about these types of surveys or data that's been collected, where we have something called false positives, false negatives, true positives, true negatives. And in statistics class, if you end up taking that course in the future, you'll talk more about the different types of errors that you can have and how much room for error you give in your studies. Okay? So in this case, what I would recommend you do whenever you have a chart of data, of information, first things first is I would do some very basic addition, basically just addition, some basic arithmetic here. I would add up the total number of each row and each column. So for example, for the total number of pregnant women, I would have 100 plus 30, or 130 pregnant people there. For the total number of people who were not physically pregnant, I add the second row, 50 plus 70, and I get 120 for that row. For the total number of the column of people who tested positive on the test, I add 150 and I get 150. And for the total number of people who tested negative in this experiment, I get 30 plus 70, which is 100. And notice that if I add now the totals across and on the column vertically, I should get the same total, if that makes sense, cumulative total, which in this case is 150 plus 100, or 250, and then vertically 130 plus 120, also 250. So in the total number of people that were in the experimental group here, or people who we collected information from in the survey, if you will, we had 250. This would be like what we would call our N, or our sample size, if we were doing a nice formal statistical analysis. Okay, so based upon this, now we are going to analyze the conditional probabilities below. The first question says, now again, the idea here is, what is the likelihood that if you picked one of the ladies from this test, that they would be in this category? That's basically what we're asking. So if I picked one of them, what is the likelihood that I picked someone who happened to be pregnant, given the fact I know that she tested positive? Pregnant, knowing that she tested positive. So using my little cheat sheet here, the little shortcut we talked about, what I would put in the denominator first is the number of people who tested positive. If you don't like the shortcut, feel free to use the original formula from our first and second slides. So the number of people who tested positive all together would be 150, right? That first column. So that would be the group that I'm looking at, only women who tested positive. Of those 150 women, how many of them were actually pregnant? In other words, how many of them got a true positive, right? They were pregnant when they happened to test positive. So how many pregnant women do we have? Now, if you wanted to look at the entire total of pregnant women, that's 130. But should that be what I do if I'm looking at conditional probability with my shortcut? No, I should only look at pregnant women who happen to have tested positive. So only looking at, I restrict myself to the condition, right? Only looking at those who tested positive here. Of the 150, how many of them were actually physically pregnant? So the test was true. That would be 100. So if you said 100 out of 150, that would be the correct setup. And then of course from here, it's just a matter of reducing, right? We can notice that they both end in 0, so it's 10 out of 15. But both 10 and 15 are divisible by 5. 5 goes into 10 2 times. 5 goes into 15 3 times. So the reduced fraction answer would be 2/3, or roughly 67%, 66.6 repeating, all right? Okay, so let's see if you can try the next one on your own, since we did that one together. What is the probability that you randomly select from this group of 250 women a woman who is pregnant, given that she tested negative? Okay, so let me erase what we did last time so we can focus in here. Okay, and I'll clean it up a little bit for you. So this was our positive people, this was our 50, we had 150 here. Okay, so now we are looking solely at this condition. Women who tested negative. So where am I looking? For my denominator here, the total number of people who tested negative, which in this case is 100. From those who tested negative, since that's the condition we're looking at, I'm only looking in that column, how many of them happen to be pregnant? If you said 30, you'd be correct. So the answer there would be 30 out of 100, which reduces to 3 out of 10, or 30% exactly. Okay. Finally, for C, let's see if you got that one right as well on your own. How did we do? What was the probability of selecting a woman who was not pregnant, given the fact we know she tested positive? So testing positive is where I'm looking this time, which would be this column, right? So we're back to that 150 number for our conditional denominator. Of those 150 women who tested positive, how many of them were not pregnant? That's right, 50. So 50 out of 150 reduces to 5 out of 15, or 1 out of 3. That's interesting, roughly 33%. Notice that these two events, both probabilities, would add up to 1, 2/3 plus 1/3, or 67% plus 33% roughly. And that is because those events are called complementary. We talked about those in previous videos, didn't we? Because being pregnant or not pregnant, those are your only two physiological options, right? She's either pregnant or she's not. She doesn't know necessarily. She's testing to find out, but this person can either be one or the other. Okay, so that's why they add up to 1. Well, let's have you try one more of these charts once you feel comfortable with this conditional probability type of problem. Last example, here we go. Can you use this table to answer the questions below? So again, it's a little hard to read, so I'm going to go ahead and clean it up for you. Here we have a situation where someone is going to buy a car, and they have two basic types of salesmen they're dealing with. Someone who's a little more pushy, and someone who's a little bit more laid back. Maybe you've had a similar experience when buying a used car. And in the end, at the end of a week or at the end of a month, we're not told which, but at the end of a certain period of time, we're told how many times a pushy car salesman made the sale versus not, and how many times the laid-back car salesman made the sale. So here's the column of sales that were actually made, and here's the column where there was no sale in that interaction. So the person decides not to buy the car from that person. In the first entry here, we're told that there are 100 times where a pushy person sold the car, while there were 250 times where the pushy car salesman did not make the sale. We're also told that there were 220 times where the laid-back car salesman made the sale and 80 times where they did not. Okay, so again, your first thing you want to do when you're dealing with any of these charts is to find your totals. So I'll take my first row across of pushy car salesman interactions. 100 sales were made, 250 no sales, which is a total of 350 interactions for the pushy car salesman. For the laid-back car salesman, 220 were sales, 80 were no sales, for a total of 300 interactions with him. And then for the sale column, there were 100 made by the pushy car salesman. There were 220 made by the laid-back car salesman, for a total of 320. There were 250 no sales for the pushy car salesman and 80 no sales from the laid-back car salesman. So a total of 330. When I add up these numbers, 320 and 330, we should be getting the same as when I add up, yes, 350 and 300. So in both cases, I should be getting 650 interactions altogether. Okay, so once you have your totals, your cumulative totals for each row, each column, and in total, now let's see if you can answer the first question with me. We'll try the first one together. If you picked one of these interactions randomly from the data, what's the likelihood that it's one where there was no sale made, given the fact we know we had the laid-back car salesman. So given the fact we had the laid-back car salesman. So according to our shortcut, that's our denominator, the number of interactions with a laid-back car salesman. So that's where we start if we're using our shortcut. So how many of those interactions are present? Well, we have this entire row here for the laid-back car salesman. There were 300 of those interactions. So in those 300 interactions, how many of those resulted in no sale? If you said 80, you would be correct. So we would have 80 out of 300. That's the setup. And then from there, it's all a matter of reducing, which you end up getting eventually 4 out of 15 if you keep reducing down until you can no longer do so. Roughly, that's about 26.7%, roughly. So almost 30% of the time, if you know you had the laid-back car salesman, it was likely going to be a no sale, which means the complement of that, if you knew you had a laid-back car salesman, it would be 1 minus that number. So close again to a little over 70% of the time he made the sale. Okay, what about the next one? It says, find the probability of selecting an interaction which results in a sale if you know, given that you had a pushy car salesman selling the car. So we start with that as our condition, don't we? That's our denominator. How many interactions did we have with the pushy car salesman? So there were a total number of 350 of those interactions, it looks like, the first row here. And of those, how many of them resulted in a sale? Did you say 100? That's what I said as well. So the setup there should be 100 out of 350 using our shortcut. Eventually that does reduce to 2 out of 7, which as a percentage is about 28.6%. So here we're basically seeing that if we knew we had the pushy car salesman, we have roughly a 29, almost 30% chance that a sale was made. So the complement of him not selling it was, again, closer to a little over 70%. So they're almost completely opposite, aren't they? Okay, let's take a look at our last one and see how you did. It says, find the probability of selecting an interaction that had involved a laid-back car salesman, given the fact that you know that there was no sale made. Okay, so you know there was no sale made. That's where we would start. How many interactions resulted in no sale? Well, that would be this column here, wouldn't it? The no sale column has 330 interactions. And of those interactions, how many of them were with a laid-back car salesman? That would be 80, correct? So your setup here should be 80 out of 330, which does reduce to 8 out of 33. Doesn't go any further than that. But as a decimal, that's roughly 24.2%. It became 0.242 as a decimal, and then we changed it to percent. Okay, so we've now shown you different ways that you can use the conditional probability formula to solve these types of questions. The first thing you have to remember is anytime I hear or see the word given or the probability of something with a line after it and then something else, that is conditional probability. And so rather than using the complicated formula of one fraction over another, I think it's easier just to zoom in as your denominator on what just happened and then what's the likelihood of the favorable outcome on top. Okay? If you have any questions, feel free to reach out to me. Otherwise, happy practicing because math is not a spectator sport. I'll see you next time.